Welcome to Lecture 12, Measuring the Intrinsic Properties of Stars. Today we are going to be talking more about the different properties that stars have, continuing with where we left off in the last lecture. If you remember this list from the last lecture, you should remember that we went over luminosity and apparent magnitude. We also talked about distance and measuring mass. Today we're going to talk more about the other parts of the properties of stars that we hadn't went over previously. So remember, properties of stars include its mass, its distance from the observer, its luminosity, which is the output of energy, which is measured in watts, its temperature, its composition, what elements is it made up of, its speed, rotation or revolution, and the physical size of the star. Well, how does a star generate light? If you remember, we talked about last time, we talked about the EM scale a little bit, and we talked about wavelengths and photons and how luminosity is the amount of energy given off by an object, or the output, which has to do a lot with temperature and how in Wien's law and all of that jazz. And we learned and spoke a lot about how heat leads to light. So heat or temperature is on a continuous spectrum, and it is electron emission or photons, which leads to the emission spectrum. So every element emits a different photon from electrons, making a different light color. So depending on which element you have, when you heat it up and burn it, it will give off a different color. For example, lithium is purple. It makes a pretty lavender color. Hydrogen is red. Calcium is red. Each one has a different type of color, and we may not be able to discern which color is which off the top, but each element will burn a different color. So when you have an emission spectrum, it will emit a photon from electrons, making a light color. So the light spectrum is a continuous spectrum of heat. Emission leads to the line spectrum, which is electron emission, and then the absorption line spectrum is then these dark lines represent energy absorbed by electrons from continuous spectrum. So if you have a cool gas, it will actually absorb certain electrons from the continuous spectrum, creating the absorption lines. This excites electrons, moving them to different levels. And so absorption and emission spectra are complementary. Both of their lines match up. If you remember, the emission line spectrum is the colorful lines that form, whereas the absorption line spectrum is the lack of lines that form, so the black lines in the colors. The spectral classification is very important for stars. So before 1900, stars were classified based on the strength of their hydrogen lines in absorption spectra, leading to the following classifications of A star, B star, C star, etc. This means the difference in appearance of stellar spectra was explained as due to differences in the chemical compositions of the stars, which is wrong. Modern science, or modern spectral classification, was created by Annie Gymkanin and Cecilia Payne, who took the temperature of a star into consideration when related to spectral lines. So if a star is cooler, its spectral lines won't actually be as defined, meaning that it may have elements that we just can't tell in spectral classification. How does temperature affect a star's spectra? You look at one absorption spectral line at a time, such as the red spectral line from hydrogen known as hydrogen alpha, which is the 656 nanometer line. This occurs when hydrogen electrons are excited and jump from level 2 or N2 to level 3 orbits. And so what ends up happening is, ooh, I'm so excited, I'm going to jump up, and that's going to release a photon when I go back down. Electron energy level transitions in hydrogen lead to different colored lights. So violet light is absorbed if it lifts the electron from level 2 to level 5. A blue-green light is absorbed if it goes from level 2 to level 4, red from 2 to 3. Ultraviolet is if they lift electrons up from level 1, and infrared if they lift electrons up from level 3. So if you have 2 to 3, and then it goes 3 up, you're going to create infrared. If it goes from the first level to above, then it's going to have ultraviolet light. This means that your electron already has to be up at a certain level in order to cause it to excite and jump from another level. But when we're looking at the hydrogen alpha, we're looking specifically for that red line, which goes from 2 to 3. So in this case, a photon is released when it goes back down. So now let's look at some examples, because the heat of the star will affect this hydrogen alpha line. So let's look at star A, which is 4,000 Kelvin, which is a relatively cool star. It will have few atomic collisions with enough energy to actually knock the electron of a hydrogen up from level 2 excited state, meaning the majority of electrons are at the actual level 1, meaning when it pops up, it will have ultraviolet light, or an ultraviolet photon, meaning there will be few hydrogen atoms that will be able to actually form this particular hydrogen alpha line, since they're not really going to be at level 2, they're going to be at level 1. So once they hit level 2, then they can move up to level 3, resulting in the hydrogen alpha line. So because there's so few opportunities for this to occur, it results in a weaker absorption line for a hydrogen alpha. Now let's look at star B, which is a relatively hot star. These energetic atomic collisions will have enough energy to knock electrons to level 3 or higher. However, there will be few opportunities for hydrogen atoms to catch photons to form the hydrogen alpha line, because most of the electrons will no longer be at level 2, but at level 3 and above. Meaning, you're going to probably get that blue-green line where you're going to go from 2 to 4 or 2 to 5, where it's going to knock up higher. The conclusion is that the hydrogen alpha line is actually weak when a star is cool or too hot. Hence, you need some optimal temperatures, such as 10,000 Kelvin, and this line will be the strongest as many electrons would already be at the second level and be able to pop up to the third. From this, you end up with a very different spectral classification that goes from hottest to coolest, taking temperature into account. This is the hottest. We don't actually use it that often, hence why it's in parentheses. And again, the coolest, meaning we don't use them as often. So these are the ones we're going to mostly focus on right in the middle. OBAFGKM, which has a very nice little way to remember it. Oh boy, an F grade kills me. That should be a very easy way to remember it. Keep that in mind. Each class is then further divided from 0 to 9. So you get 0, 0, or O0, O1, O2, O3, etc., etc., etc. With 0 being the hottest to the coolest. The hotter the star is, the less absorption or emission lines are visible to be seen, whereas the cooler the star, the more lines, but also the wider and less sharp they will be. We can observe here the differences between B, G, and M types in their wavelengths. B types are hotter and so have more energetic wavelengths, whereas M types, being the coolest, have longer wavelengths, meaning the spectral lines will be more, but less sharp. Here is the B type and the M type, and what we can see here is, here's a spectral line. It's kind of hard to see, right? So it's not that it doesn't exist, it's just harder to see. Versus G type, where we can see them much clearer. And then we get to M type, where they're not as sharp, they're much wider, which we can see down here. And these are all the different lines. The continuous spectrum means that all colors are present. And this has to do with the composition of and abundance. So there are 3 types of spectrum that we have learned about so far. The continuous spectrum, which is where we see all the colors of the rainbow. Ta-da! This is normally produced by a hot solid or hot dense gas. And then we get the emission spectrum and absorption spectrum. These are how we tell the composition of an object. An emission line spectrum generally is produced by a hot low density gas, whereas an absorption line spectrum is the result of light with a continuous spectrum passing through a cool gas. Emission line spectrum implies that the atoms or molecules are well separated and the atoms are hot enough to have excited the electrons to higher energy levels, and isolated atoms or molecules all behave essentially identically, emitting light only at the specific wavelength associated with their particular set of energy levels. Usually this is produced by hot, low-density gas, which is our emission line spectrum. Absorption line spectrum is produced when light from a hot, dense body passes through the cooler gas between it and the observer. In this case, nearly all the colors are present, but light is either missing or much dimmer at the specific wavelength corresponding to energy. What we saw on the previous slide was an absorption line spectrum, in which case, on some of the star types you had black lines, and in others it was just a dimmer red line or a dimmer blue line. I personally think emission line spectrum are much easier to read because the colors are a little more crisp and easier to determine. but that's just my personal feelings. Anyway, absorption line spectra are most seen with star spectra because they are produced by cooler, lower density gas lying above hotter layers, meaning you have your hot star and then the outer layers of the star are cooler, allowing for absorption line spectra to create. The cool interstellar gas clouds between a star and us can also produce absorption lines in a star's spectrum. Composition here is very important because different elements have different spectral lines, basically like a fingerprint. So the absence of a spectral line doesn't always mean that it's missing that element, rather that it is due to the temperature of the object keeping the line from forming. Okay, remember that if it's too hot, you're not going to have a strong hydrogen alpha line, and if it's too cool, you're not going to have a strong hydrogen alpha line. This is identified by the width of the spectral line and its brightness for emission or darkness for absorption. The more of an element there is, the wider and stronger the spectral line, and the temperature is more critical in determining what we see here. Temperature is super important in what we are going to see from a star. For example, its color. Temperature will determine the light emitted by an object, because remember, the hotter it is, the more energy is being produced, and this is not necessarily the reflected color. Remember we talked about range ovens earlier. When you heat it, the metal coil turns orange. The same thing happens when you have a fire. The hotter the fire, the bluer the color, and that's because the more energy it has, the shorter the wavelength. With spectra, it really impacts the classification that we get. Remember when we were talking about temperature, hydrogen alpha lines, if it's too hot or too cool, it messes with it. So by examining the intensity or the width of the spectral lines and how crisp it is, or dark and light, and the number of lines allows us to determine spectra, okay, or spectral classification. Using color to determine temperature causes issue, meaning it's not a good indicator because the color of a star isn't necessarily the reflected color. The temperature may change the color, and then other things can happen in between. So temperature may say, okay, here's our temperature, it should be blue, but things will happen between us and the star that will end up changing the color, meaning atmospheric windows. Only visible color will pass through our atmosphere. This makes it not very appropriate for very hot or very cool stars. We also have this other thing called interstellar reddening, basically space dust. It blocks more blue light than red light, making stars appear redder than they actually are. For example, our star would technically be green, but because of our atmosphere blocking out certain colors, we see a yellow sun. Next, we're going to talk about the motion of stars. And there's two types of motion, the radial motion and the tangential motion. The radial motion is when stars move closer and farther from us as the observer. The tangential motion is when stars move parallel to the observer, or left to right in our situation. Radial motion is very important because it leads to the Doppler effect. In the Doppler effect, when you move away, it causes a red shift, versus when it moves closer, it causes a blue shift. And this has to do with wavelength, and we tend to hear this the most with sound. Sound is our best example of the Doppler effect. So you're driving, and you hear a siren. As the siren comes towards you, the sound is one way, versus when it's right next to you, and when it's moving away from you, it has a very different pitch. And we know this very well. We know when a siren is moving towards us and away from us based on the pitch it is creating. And that is because the sound waves will shorten, creating a higher pitch as it's moving towards us, and it will lengthen or stretch, causing a lower pitch to form as it's moving away from us. And the same thing happens with color. As it is moving away, your wavelengths will actually lengthen, causing a reddening to form, versus when it is coming towards us, it will actually shorten, causing it to become bluer on the spectrum. Whereas, in fact, it might be just between it, being more like here, which we're going to pretend is green. So let's say this wavelength means our color would be green. As it is moving towards us, it would appear more blue. And as it is moving away from us, it may appear more orange or red. Green would become yellow, which would become orange, which would become red as the wavelength gets stretched farther and farther. And then as it gets closer and closer to us, it would appear more blue as the wavelengths are compressed. Only radial motion causes this, not tangential motion. This has nothing to do with distance. It only has to do with the amount of shift. So shift forward and shift back, which is proportional to the object's approach and recession speed. This is where speed really comes into play. Tangential motion, on the other hand, is measured by an object's proper motion. And this actually changes the right ascension and declination on the celestial sphere in the night sky. Let's look at the Big Dipper. The Big Dipper has changed. It used to look like this in image 1. And over time, it became like this. The greatest proper motion is actually in Bernard's star, which moves about 10 inches per year, which we do see in the Big Dipper, which is the star, which is pretty neat. So remember, tangential motion is when it moves parallel to us. So it results in changes on the celestial sphere itself. It doesn't cause a blue shift or a red shift. It literally causes it to appear to move in our night sky, changing things that we have recognized on the celestial sphere as constellations. The rotation and revolution of a star is also very important, and this is measured by looking at the star's red and blue shift, or its Doppler broadening, which can also be measured with spectral lines of an object, the widening of the spectral lines, for example. And if the spectral lines double or split, it means there are two stars revolving around each other. So here's an image of a binary star as a single smear. Okay, so the observer on Earth sees the combined light of both stars, and spectral lines are doubled in combined spectrum as seen on Earth. Doppler broadening is something that happens as a star is rotating or moving towards and away, causing gas atoms to have different radial velocities, which results in the widening of spectral lines. The mass of a star can be determined with a binary or multi-star system best. The concept about this is we observe the motion among star forces, and we use a variation of Newton's third law, which is ma plus mv equals k squared astronomical units over p3 of years. And this is the sum of the two masses, which can be found from a period or orbit and separation. From this, we can actually observe the distance between them, and since the gravitational force is dependent on the distance of two objects and masses, if you know the force and distance, you can therefore determine the mass of the star. And essentially, you work backwards. We've been talking about binary star systems for a little bit here now, and this is where this is going to come into play. Binary stars are pretty neat, because gravity actually holds the stars in orbit around each other. Their gravity holds themselves. And there's two types of binary star systems, and that's the apparent double star and the true binary. So the apparent double star is when two stars lie in the same direction, appear to be double stars, but don't actually orbit each other. An example of this is Alcor and Mizar from the Big Dipper, where the stars are on the celestial sphere, located right next to each other, but in reality are many light years apart from each other. A true binary system is when you have two much closer stars that actually orbit around one another with gravity holding their orbit, like here. The example is Mizar. Mizar is a true binary star because the two stars are Mizar A and Mizar B. We can observe the binary system's orbital motion by comparing images that are years apart from each other. And if you can see two separate stars and their individual motion, it is considered a visual binary star in this case. Some binary stars are so close together that their light blends into a single block, even to the most powerful telescopes. And so in this case, instead of viewing motion, you actually look at its spectra. As each star moves within its orbit, it moves towards and away from Earth, creating a Doppler shift for both stars, which means there are two sets of spectral lines, and they are relative to each other. One will have wider wavelengths due to moving away, and one will have shorter wavelengths due to moving toward us. And this is known as spectroscopic binaries because we looked at the spectroscopy. You then have eclipsing binaries. These are pairs of stars whose orbits are oriented edge-on with our own line of sight, causing the stars to eclipse each other sequentially, creating a variable brightness. And from the duration of the eclipses, scientists can actually determine their masses and their sizes. If it's both eclipsing binaries and spectroscopic binaries, it allows for parameters to be determined for the system way better than for non-eclipsing spectroscopic binaries. And this is because scientists then know the orientation of their orbits, allowing them to know whether the Doppler shift reflects the full speed of orbital motion instead of just part of the motion that occurs along our own line of sight. Now we're going to move on to stellar diameter. So when you look at the image of a star, you measure its angular size. its luminosity class, or spectra, is divided up into, class 1A, 1B, 2, 3, 4, and 5. And the stellar luminosity class is based on its spectra. So if a star is huge, it doesn't have much interference, it has small and narrow and sharp absorption lines, it's probably a supergiant, so it's class 1. Whereas a medium star is a giant, which is class 3. And then you have class 5, which is small stars with more interference, wider absorption lines, and they're probably more along the lines of main sequence stars and dwarfs. Some stars will have the same spectral class and same temperature, but be different sizes completely. Larger stars will have slightly narrower, better defined spectral lines because they have less internal pressure. With eclipsing binaries, if you take a picture and study the split spectra, you can determine the diameter of the star and how long the eclipse occurs. So we know that the moon is the size it is based on studying eclipses and knowing that it's a sphere, and so based on a lunar eclipse, we know that it has to be a certain size, etc. So you're actually able to determine the diameter of the moon and the sun based on that. With temperature and luminosity, we're revisiting this again, we actually use Stephen Boltzmann's law, where a star's luminosity is directly related to its surface area, 4 pi r squared. And you can get luminosity by multiplying it by the energy radiated to the surface area, which becomes L equals 4 pi r squared times theta t to the 4th power. If you increase the temperature or the radius of the star, it is more luminous, and the same is vice versa. And you can use this equation or the HR diagram to determine a star's temperature and luminosity. And we're actually going to talk about the HR diagram more in the next lecture. That is all for today. If you have any questions, please feel free to post them in the discussion board. I'm more than happy to work with you and answer them. If you had trouble filling in any of your study guide, again, questions go there. I will be there to answer them. Otherwise, I'll see you guys later.